Hi, I am Nilanjan Mukherjee from Mentor, a Siemens business. I'll be talking today about a paper that we presented at the International Test Conference 2019 at Washington, D.C. This paper describes a feature called Observation Scan that we recently released as part of Test Tools to address some of the in-system test challenges for automotive ICs. As we all know, the electronics content of cars have been increasing at a significant pace. It is expected that by 2020, 35% of the total cost of a car will be attributed to electronics. This number is predicted to rise to 50% by 2030. As the electronics content is gradually rising, there are some extreme requirements related to high quality and long-term reliability of automotive ICs targeting safety-critical applications. All automotive-related electronic systems are governed by functional safety standards such as ISO 26262. Additionally, automotive ICs need to be certified to various safety levels, also known as ASIL, depending on the application for which the IC is being deployed. The purpose of this paper was to present a logic BIST technique for automotive ICs to address some of the challenges that are showing up for in-system and in-field testing. Typically, logic BIST is deployed during key on and key off, and optionally when the system is in functional operation. It is critical that the tests that are run during those phases have to finish within an extremely short test window. It is also important that within the short test window, the defect coverage should be at least 90% in order to get an ASIL D certification. There are some strict power requirements as well, such that the test, when run when an IC is idle, shouldn't interfere with portions of the system that are operating in functional mode. Finally, shortening the test time also has a positive effect on the aging process. In this slide, we present the overall observation scan architecture. As you can see, it is based on the typical stumps architecture for logic BIST. At the input side, there is a LFSM that operates as a decompressor during ATPG, whereas it operates as a pseudo-random pattern generator in logic BIST mode. Similarly, at the output side, there is a spatial compactor that directly drives the channel pins during ATPG, whereas the spatial compactor drives the miser in logic BIST mode. Control and observe points are a necessity during logic BIST to improve the overall random pattern test coverage. In observation scan, we are connecting the observe points in separate chains and allow them to capture circuit responses not just during capture, but also during the shift cycles. One of the questions that arise, how is the scheme different from techniques such as circular BIST? There is a fundamental difference between the schemes. In circular BIST, the scan cells were not only capturing responses, but also driving combinational logic during shift. This creates a sequential dependency between subsequent shift cycles, thereby making the fault simulation extremely complex. In the proposed scheme, the observe points are only observing the test responses and don't provide any stimuli to the combinational gates. This reduces the complexity of fault simulation. This slide shows the structure of the observation scan cell. Instead of one 2x1 mux, we need a 4x1 mux with two select inputs. When the select inputs are 0, 0, the scan cell operates in the normal functional mode. When the select inputs are 1, 1, the scan cell captures during shift, thereby behaving as a long compactor. When the select inputs are 1, 0, the structure operates as a regular scan cell. In other words, M2 equal to 0 disables the shift and capture operation. When the select inputs are 01, the scan cell is in capture mode, where the Q output is XORed with the circuit response before being captured. This is necessary to preserve the fault effects that are captured in observation scan cells during shift. This slide shows a pictorial representation of the fault simulation task. Note, the regular capture patterns are termed as parent patterns, whereas the shifted version of the responses are termed as intermediate patterns. The first pattern, P0, results in a response R0. Every successive shift of the response R0 results in a new intermediate pattern, B0N, until the parent pattern P1 is entirely shifted in. Similarly, the responses R1 for parent pattern P1 will result in multiple intermediate patterns B10 to B1N. The process continues with the third pattern P2 and so on. If you now look at only the observation scan patterns, there is a parent pattern B0 followed by intermediate patterns B00 to B0N. Similarly, there is a parent pattern B1 followed by intermediate patterns B10 to B1N, and so on. In summary, the number of intermediate patterns is directly proportional to the length of the longest scan chain. However, logic-based patterns are amenable to distribution. Therefore, parent as well as the intermediate patterns are distributed to multiple slaves, thereby speeding up the fault simulation process. The next challenge is to calculate the miser signature for all these patterns, especially when they are distributed to numerous slaves. Fortunately, since miser calculation is a linear process, each one of the slaves are responsible for calculation of the signatures for the parent and intermediate patterns. And once they are calculated, they are sent back to the master, where the final miser signature is calculated based on simple principle of superposition. Now I will show some results for 10 industrial benchmark designs, varying from 1.1 million gates to over 14 million gates. The number of scan cells, scan chains, and the length of the longest scan chain are presented in the third, fourth, and the fifth columns. We collected a lot of data related to test coverage improvements and silicon area savings. But this is the most important slide, as it shows the pattern counts needed to reach 90% test coverage with and without observation scan. The first set of bars on the left side shows how to read this graph. If the pattern count for baseline and observation scan are the same, the length of the gray and blue bars will be the same. On the other hand, when the pattern count for observation scan is 2x less than the baseline, the gray bar is twice as long as the blue bar. Now if you look at the pattern count results for the 10 industrial designs, you'll notice that with observation scan, the pattern count decreases anywhere between 2x to more than 16x. On an average, there is a 9x reduction in pattern count, which directly translates to test application time savings. In conclusions, observation scan helps in significantly reducing the LBIST pattern count for in-system testing. It gives one the flexibility to optimize between the test application time and silicon area overhead. It also helps one meet the stringent time requirements for logic testing during key on, key off, and online monitoring. Thank you for your attention.